Good morning, everybody, or morning for me. We're going to continue on with more vectors here. We're going to look at a few different things today. One of the things we're going to look at is spanning sets, and we're going to talk about collinear and coplanar points. But one of the things I want to do first is going to be how to sketch a parallelepiped. Now, you've heard me say those words before, but what we're going to do now is we're going to look at how to do that. So let's get that going. Hope everyone is well today. It's annoying you can't change the default line width unless your computer is hooked up to an actual smartboard. It's frustrating. Okay, so I'm just going to say, I think this is vectors day 5. I don't know, vectors more. And so right now we're going to look at a no, I spelled that wrong. Parallelepiped. I think I spelled that wrong as well. Anyway, it's how it's pronounced. Parallelepiped. Probably an O in there. Parallelepiped. Yeah, that looks like it. What we're going to do is we're going to sketch this. So a parallelepiped is a shape that is described in 3 space using 3 non-collinear vectors. And so that doesn't really mean very much, but what we're going to do is we're going to sketch it, and that will add some depth of understanding to what's going on. Okay, so I think I'm going to probably even make this one bigger because it's good to have more space than less space when we're doing this. So here we go. So I'm going to define a parallelepiped according to 3 vectors. And so I think what I'm going to do, whatever, doesn't matter. Here we go. So imagine that we had vector A, and vector A was -2, 2, 5. -2, 2, 5. And then vector B is going to be 0, 5, 3. And vector C is going to be, how about 0, -3, 4. Okay, so there are 3 vectors. And so first thing I'm going to do is I'm going to just sketch these. Now, I'm not going to add in the rectangular prisms that add definition. I'm simply going to go ahead and sketch these in roughly. So we're going to have, there's my x-axis, my y-axis, my z-axis, and so on we go. So what we have is -2. Okay, so back 2, 2, so over to the right 2, and then up 5. So 1, 2, 3, 4, 5. So in about here. So I'm going to go ahead and I'm going to do, let's do blue for A. So let's sketch that in like that. So there is going to be vector A. And then let's take and we'll make red for vector B. So vector B is 0 on the x and y, or on, excuse me, on the x-axis, 5 on the y. So over here 5, and then 3. So 1, 2, 3. So in about this vicinity here. So let's draw that fella in. So let's sketch that. And then C can be, I think I can select green. I think that's maybe green. Oh, I don't know. Is it green? I don't know. So actually, I want my pen. Sorry. What was it? Was it that? Okay. So 0, so not back and forth at all. -3, and then 4. So, you know, in about here. So let's sketch that vector in. That color there. There we go. Is that green? I think it's green. So you look at that and you might think, well, how on earth does that define anything? It does not define a 3D shape. Well, it sort of does. So again, with the magic of our smart notebook. So I'm gonna kind of show you how we can do this. So I'm gonna grab this and say, okay, I'm gonna start by making the plane that these 2 vectors define. Okay, so what I have there, if you think about, you know, these two vectors, the red and the green, it has formed a plane. Okay, you're like, oh, okay, all right, fine. So I'm going to make another plane now. I'm going to make a plane with the red and the blue. So there's the red, and there's the blue. And so now I've formed a secondary plane with this. So you can kind of think about this now. You're like, oh, you can kind of see how, that's two sides. There's this side of a box and then this side of a box. And then I'm going to form the plane that is made with the green and the blue. Okay, so clone that guy there. And clone this guy here. Stop that. Stop that. Okay, there we go. And so now we've kind of got like the bottom of a trough, the bottom of a trough, and the floor of a trough over here. And so we've kind of fully outlined now three different faces to this. Um, you know, it kind of looks like your mind can shape it as a rectangular prism. It's not necessarily rectangular. In fact, I'm pretty confident that it's not, because none of those things likely has a 90-degree angle. Although when we force perspective like this, it's hard to tell. We're going to get to a point where we'll be able to find the angle between those vectors in 3 space, and we can demonstrate that it's not a rectangular prism. Or maybe it is. Maybe I just got lucky, although that seems really, really unlikely. So let's keep going. So we're going to fill in the other edges of this box. And so I just keep on, finding and forming the planes that each of these pairs make up. And so we're most of the way there. And then we're going to clone that. And there we go, right? So what we've got there is a parallelepiped. And so it is a three-dimensional shape that, is going to have parallelograms on each of its faces. Sometimes, although it's hard to do well, particularly, in this thin dimension, I'm going to, shade in one of the faces, and it kind of helps you see, right? So if we look this face here, well, I haven't done a good job. So here is a face, right? And I would have changed the opacity if I could have. But there is one face, and then if I grab another color, this color, there is another face, right? And so if with the context of being able to see that, you can see that there's a three-dimensionality to it, and soon enough we're going to learn how to find the volume of a parallelepiped and the surface area of a parallelepiped. So yeah, it's an interesting exercise being able to draw those things. It's something that it's worth practicing, because drawing stuff in 3 dimensions for some of you is going to be a challenge. For some of you, you're all over this. So anyways, there you go. So that is a parallelepiped. Now, what I'd like you to do, pause the video right now, or not right now, but in a moment. I would like you to try, if you can, to determine what the coordinates of each of these labeled vertices is. And it's a really good exercise to try and figure these things out. There's only one vertex, right? 1, 2, 3, 4, 5. Yeah, there's another one that's kind of hidden back in there. I'm not going to worry about it, but go ahead and see if you can figure out what the coordinates of each of these vertices is, and then we'll try and figure it out. Okay, so it's hard to see with all this stuff on there. I'm going to actually, after all of that, gorgeous coloring that I've done, I'm sure you can all, attest to how lovely this is. I'm going to pull those out, and maybe I will label that other vertex back there. Yeah, here we go. So this guy here. So I'm going to take a moment now, and I'm going to label each of those, the primary things. So this point, this is an easy point to get to, right? Because this point followed vector C out. So vector C, you could also think about as being vector O C, because it starts at the origin and goes out to that. And so that right there, that's the coordinate of that point. It is 0, -3, and 4, right? So that's that point. Easy enough. This point down in here, right there, that's, well, that just followed vector A. So that point right there is, of course, -2, 2, and 5. And then this point over here, obviously, is this guy, and it is 0, 5, and 3. Okay, so those are sort of the gimmies. They're easy to get to. Let's consider the other ones. Well, let's look at this point right here. Well, this point, it's not that bad, because what did we do? We followed one of vector B, and then on that we added a vector A, right? And you can see that because it is tail to tip, and it continues there. So it starts from the origin and it gets out to here, and we could do it two different ways. We could either add vector A and then vector B to get there, or we could add vector B and vector A, and that's because addition is commutative. It doesn't matter the order that we do it in. So the coordinates of that is going to be the sum of those two vectors. So this is going to be -2, 7, and 8. I can't see that from the stuff in behind it. So let's move this. There we go, right there. And that's lovely. And so there it is. Now let's think, if I were to say, go ahead and plot. So this is not a perfect method to check and see whether you've done this correctly, but it's a decent method. So if you've done a reasonable job of sketching your points, which I'm not sure that I have, imagine that I said sketch the point -2, 7, and 8, and hopefully you'd end up in that vicinity, right? So -2 would be like boot doot, and then 7 would be like 1, 2, 3, 4, 5, 6, 7, and then 8 would be 1, 2, 3, 4, 5, 6, 7, 8. So not in the exact spot, but certainly reasonable, right? So that's a good way to check. All right. And so then how about if we wanted to get to, this point up here? Well, this point we can follow one green, one blue. So we can add up a OC and an OA, or an A, and we would find that the coordinates of this point are going to be -2 plus 0 is, of course, -2. And then -3 plus 2 is -1. And 4 plus 5 is 9. Now, it sort of looks like it's riding on the z-axis there, but it can be projected in behind. And in fact, if we thought about it, so like -2, -1, and then 9. So yeah, like it's in the right vicinity. So we can follow that pattern. This one up here, well, how would we get to this one up here? Well, this one up here, this point, we went across a green, across a red, and across a blue to get us there. So it's as far away from the origin as any point that we're going to have. And that means we just need to add those three things together. Alternatively, you could say, well, I just added a green to this point to get there. And that would be lovely. I'm just going to look at this and see if were I to add this up, it would be -2. And I guess that would be 4 and 8, and so 12. So the coordinates of that point are -2, 4, and 12, right? So this is sketching some stuff in 3 space, a bit of understanding. So yeah, good stuff. So on we go. Next thing we're going to look at, something now called spanning sets. So here we go. That's what I want, right? Spanning sets. Okay, so spanning sets. Think about spanning sets as being, if we think about it in 2 space, if I give you 2 vectors in 2 space, can every other point or vector in existence be expressed as some linear combination of those 2 given vectors? And so I'm sure that doesn't mean much to many of you, but imagine that we said this. Oh, that's not really the right color for an axis, but let's pretend that it is. So there are my axes. They're terrible axes, but nevertheless, they're axes. Imagine I gave you the following 2 vectors. I said, all right, you've got 2 vectors. You've got, let's change the color here. This vector here, we'll call it vector A. and this vector here, we'll call it vector B. So here we go. So we've got vector A and we've got vector B. And I would like to know, hey, do vector A and vector B form a spanning set? And what that means is if I gave you any other vector in 2-space, could we write some combination to demonstrate that the new vector is a linear combination? So, given a vector, I'm just going to call it C for this, can we write C as a linear combination of vectors A and B, i.e., what we're really looking for is, can we demonstrate that C is equal to M times vector A plus N times vector B, where M and N are members of the reals. So conceptually, if I came along and I said, here's vector C. Vector C is going to be this color, and here's vector C. There's vector C. Is there some way that we could make a combination of these vectors such that we can describe this, right? So, conceptually speaking, I'm going to use my mouse so I can do it more quickly. If I said, here's this vector, there's this vector here, and I'm going to grab this vector here. Now it's going to not work out perfectly, but you can imagine that if I said, all right, well, I'm going to just take, not you, get out of the way, a bunch of these, and I know I'm going to need a bunch of them, and go up to here, and then go up to here, and then some of these. So, there, and it's like, all right, well, I would need more blue, so maybe I'll put another blue out here. Now that's going to be too many, but maybe it would be 1, 2, 3, 4, maybe 4 1/3 of A plus, well, maybe more than that even. So how about like 2 there? Right. So I don't need all that. So maybe it was, 2.5 B's plus 1, 2, 3, 4, 5, and maybe 5 A's. So, in this case, we were able to demonstrate that was, A and B could be used. You could make a linear combination of A and B to determine vector C. So what we're going to do is we're going to look at that. That's the concept behind it. And we're going to look at some algebraic realities of it now. So, so here's an example of what we would do algebraically for this. So let's look at this one. So show that the vector A, which is going to be equal to 4, 7, can be written in terms of the vectors -1, 1 and 3, 5. And so that's what we want to show that this vector can be written in terms of these two vectors. And so, okay, so we're gonna try and do that. So what we need to really do is we need to demonstrate the following. We need to demonstrate that 4, 7 can be written as a combination of A times, or not A, we use that variable up there, M times -1, 1 plus N times 3, 5, where M and N are members of the reals. So to demonstrate this is algebraically, this is what we're going to need to do. Well, this is the x-coordinate, x-coordinate, x-coordinate. So one equation we can get out of this is we can say, well, 4 is equal to -M plus 3n. So there's the kind of the x, and the x. And then, we're going to do a similar equation for the y's. We're going to say 7 is equal to m plus 5n. And so there are two equations. So two equations, two unknowns. Welcome to grade 10 again. Here we go. We're going to solve this. So go ahead and solve it. It'd be good practice for you to do it without just watching me. I'm going to solve it with elimination because that's dead easy to eliminate. So I'm going to add. So that's going to be 11 is equal to 8n. So divide by 8, and we have that n. That's not an n, that's an m. N is equal to 11 eighths. So we need to find out what m is as well. So I'm going to substitute back into this equation. So we're going to say 7 is equal to m plus 5 times 11 eighths. So we're going to go with eighths. So this is 56 eighths minus, I guess, 55 eighths is equal to m. So that means that m is equal to 1/8. Okay, so we have demonstrated, we have shown that the vector 4, 7 can be written as a linear combination of the vector -1, 1 and 3, 5. And what we would do is I estimated that it was, not quite 5 of the one and nearly 3 of the other. And so, that was a different example. Ha ha ha. But this is saying that we would need, where are we at? So 1 1/3-ish of vector n and only a little wee bit of vector m, and we would be able to demonstrate that we've got that there. So that's lovely. So a definition, a more formal one, like this is a a loose definition. I'm going to kind of formalize this definition. Yeah, let's do it with the fancy pen because my writing is terrible, but this makes it a little marginally less terrible. So a spanning set of vectors is a set such that every vector in R2 may be uniquely written as a linear combination of the vectors within the set. Now, in class, I'd give you some time to collaborate and think, not very long, about, well, at a glance, what would you be looking for to demonstrate that if I gave you two vectors, they didn't form a spanning set in R2? So imagine that I just gave you two random vectors. If you gave me two random vectors, it would take me no more than, depending on how miserable the numbers were, not much more than probably 5 seconds to decide whether those two vectors formed a spanning set. So think for that for a moment, kind of come up with an idea of what we would be checking for, or alternatively, think about what would cause it to not be a spanning set, right? So what would cause it to not be a spanning set? Well, hopefully you've pinned down on the idea, and it's kind of easy to figure out if we do a diagram of it. So if we had just a really basic, two vectors, if I gave you one vector of the set and said, here it is, there's one vector of the set. What's the only type of vector that I could give you that would make it not a spanning set? Well, if the other vector I gave you was parallel, that would mean we could only traverse back and forth on that line. So it's not exactly parallel, but let's pretend that it was. So any vector that is collinear or parallel would mean that this would not form a spanning set. If it deviated even a little bit, that would mean that we could eventually, with some combination of those two vectors, get to anywhere on the Cartesian plane. Certainly, if they're perpendicular, that's the most efficient. But as long as they are not parallel or collinear, they're going to form a spanning set, right? So that's important to acknowledge, and I'm going to just write that down. So, good. So any two non-zero, non-collinear vectors form a spanning set in R2. Okay, so any two non-zero, non-collinear vectors form a spanning set in R2. Okay, and that should ring true to you. That should appeal to your sense of logic and just common sense. Awesome. On we go. That's not working as well as I would have hoped. So let's go back to just a regular pen. Now we're going to talk about collinear in R3. Now, I guess before I progress, spanning set in R3 is different, and certainly three vectors in theory, like if we look at the I, J, and K vectors, they form a spanning set of all of R3. But it's more complex to decide whether three vectors are a spanning set in R3. And you can't just see whether any two of them are collinear, because and you don't need to write this down. We're gonna talk about it again, but I think that it's worth acknowledging. So imagine that I gave you two vectors already. So any two non-collinear vectors define a plane in R3, right? So if we had this vector and we had this vector, they would form a plane in R3, right? And so we could see that because we could say, all right, so if I did this, these guys are going to form a plane, right? So there's the plane. Now, if I want to be able to get elsewhere, so like this is, I'm making a flat motion with my hands right now. If this forms a plane, I want to be able to get off of that plane. I'm lifting my pen up and pushing my pen down. And you can imagine that that's the case. Well, I can add a third vector that's not collinear to either one of those two and still not necessarily get off the plane, right? So if we had one that just went like this, it could be contained entirely. It could be parallel to the plane that is defined by these things, right? So it requires us a bit more, like there's different ways that we can demonstrate this. Some of them much more trivial than others, but hopefully it squares in your mind that three non-collinear vectors don't necessarily make a spanning set in R3. So we're going to come back to that. So that's why we're jumping onto collinearity in R3 and not jumping to a spanning set in R3. So I'm going to just take that and move it off to the side. All right. There we go there. Lovely. There is a hairy woodpecker, what is that? That's a red-winged blackbird and a goldfinch at my bird feeder right now. What a lovely day. Okay, on we go. So collinear in R3. So I'm just going to, again, jump into the examples here. So what I would like to do is we want to determine whether the points, A at 1, 6, -2, 1, 6, -2, B, which is 3, 3, 1, and C, -3, 12, and -4, determine whether the points those are collinear. Okay, so we want to know whether they're collinear, and what that means is basically, do they lay on a single line, right? So if we took some random line in 3 space, um, so we got some random line in 3 space. There it is right there. What we're asking is, do all 3 of these points reside on the same line? Okay, which is a bit more of a challenge to think about. And so again, I would encourage you to think about how we might go about demonstrating that. Okay, so here's how we could go about demonstrating that. Maybe I'm going to drag, no, I'll redraw. If we took and we said, all right, so we've got this line in R3. That line again, here it is. So here's a line in R3, and I want to know that these 3 points are either all immediately on that line, or any 2 of them can be on the line for sure, because if I give you any 2 points, you can make a line that connects those 2 points. That's not a challenge. But knowing whether the 3rd point is in fact on that line is a bit more of a challenge. So here's what we would do. We would say, if I've got one point that's here and another point that's here, I'm going to find the vector that goes between those 2 points. I'm going to say, all right, well, this is the vector. So remember, we talked about a vector that's not OA or OB. This could be a vector that was AB, right? We want to see that the vector AB can continue along its pathway and get to point C. Okay, hopefully that makes sense. So I'm going to write a definition here, and we're going to hopefully see how this can square away with the definition. Okay, so let's think of them. I want 3 points in R3 are collinear if and only if, so the dreaded double if, the vector AB is equal to some scalar multiple of the vector BC. Okay, so that's assuming that the 3 points are points A. Oh, that's a bad representation of that. So given the points A, B, and C are points in R3. Okay, so what it's saying is, if I create this vector that goes from point A to point B, so that's going to be the vector, obviously, AB. And then if I find another, so I've got another point out here, and maybe it's on the line, maybe it's not on the line. For our purposes here, let's say that it is on the line. We're going to hope that. There. And so this now is vector BC. So here we go here, and then this, yep. So there's C. So this would be vector BC. What we want to do is we want to demonstrate that BC can be written as some scalar multiple of AB. So really, this is showing that these 2 things are collinear, because that's also the definition. Sorry, are collinear of the vectors. And so it's interesting. This could be written differently, and maybe some of you could see this. Another way that we could demonstrate it, or that the vector AB can be written as a scalar combination of the vector AC, right? Because AC needs to be collinear with AB as well, right? So there are different ways to think about it, and either one of those is acceptable. So back to the point at hand, as it were, is we are going to figure out what vector AB is and what vector either AC or BC. Okay, so I'm going to just make a copy of those so that I can see them more easily down here. You come here. Why are you not doing? Okay, whatever. Okay, clone that. Copy that. Come down here and paste it. Okay, so vector AB. Now, I think I've mentioned this before, but I'll reiterate. Vector AB, there is, it's always the tail minus the start. So it will be 3 minus 1 and get 2. And it would be 3 minus 6 and get negative 3. And it would be 1 minus negative 2 and it would be 3. That's absolutely one way to think about it. But I'll admit, I always just think, how do I get from 1 to 3? Oh, I add 2. How do I get from 6 to 3? Oh, I subtract 3. How do I get from negative 2 to 1? Oh, I add 3. Right? So that's certainly a less formal or a less rigorous way of thinking about it than the formulaic. It's the tail minus, or the head minus the tail. But I find it squares in my brain a little bit easier. Right? So then I need vector. I'm going to go BC. And so to go from 3 to negative 3, we're down 6. To go from 3 to 12, we're up 9. To go from 1 to negative 4, we're down 5. Ooh, I put a line there. I shouldn't have. There we go. So B, C. So negative 6, 9. Oh, did I copy that down wrong? Oh, I did. Okay, well, never mind. All right, all good. So now, so what we want to demonstrate is it's collinear if and only if AB can be written as some scalar multiple of vector BC, where K is a member of the reals. So I want to show that 2, negative 3, 3 is equal to some K multiple of negative 6, 9, and negative 5. So, it's interesting. Like, hopefully you can look at that and you can immediately diagnose that no, it's not. But for those of you who aren't seeing it, let's set up our equations. This actually will generate for us 3 simultaneous equations. We have that 2 must be equal to negative 6k. That comes from the x's. And then from the y's, we have negative 3 is equal to 9k. And then from the z's, we have that 3 is equal to negative 5k, right? So all well and good. Let's just go ahead and we're going to solve. So I'm going to divide by negative 6, divide by negative 6. And we get that k is equal to negative 1/3. So that's the only option for k. The only way that these 3 points can be collinear is if the k is consistent for everything. Go ahead and keep going. Divide by 9, divide by 9. And we're going to say that then k is equal to negative 1/3. And it's like, huzzah, they actually match. So I'm feeling pretty good. And then we progress to this one, and we're going to divide by negative 5. We're going to divide by negative 5, and we're going to find out that, dang it, k is equal to negative 3/5, which they do not equal one another. So because that k is not consistent, okay, so because, upside down therefore is a because k is not consistent, these points are not collinear. Okay, pretty cool. We've just demonstrated that those points are not collinear. All right, last piece of this particular lesson. We're going to talk not only, so we've talked spanning sets, we've talked collinear in R3. Now what we're going to do is we're going to consider coplanar in R3. Right? I'm going to go back and I'm going to grab that diagram that we had back here because I think it would actually be useful for what we need over there. So I'm going to copy that and put it in here. Oh, it doesn't work like that because it isn't a smartboard. Right click, paste. All right, so any two vectors that are non-zero, non-collinear are going to form a plane in R3, right? So the blue and the green form this plane here, and even though I only defined this little, diamond or kite shape or parallelogram shape, what we actually have is this could continue, right? So if I, if I wanted to, I could get to a spot down here by, adding negative versions of those. But we, to show something is coplanar, want to know that the plane that is defined by the green and the blue, this red lays upon that plane. Again, we're going to have different tools to do this going forward, but I'm going to show you, and again, this is good for depth of understanding, another way to do it. This is not the most trivial way to do it after we've done more learning, but it's effective for us to groom our depth of understanding. Okay, so here we go. So determine if the following three vectors are coplanar. Okay, so we want to know if they are coplanar. So here are my vectors. I'm going to have vector P, which is equal to -4, 5, and 3. Vector M, which is 6, 3, and -1. And vector N, which is 3, 5, and -4. Okay, and so if I want to know that these three vectors are coplanar, what we're asking is that any one vector can be written as a scalar combination of the other two. So we could say P is equal to A times M plus B times N, or we could say M is equal to A times P plus B times N, or we could say N is equal to A times P plus B times M, right? So any two of them can be formed to decide, how we're going to get the third vector. So, in reality, there are lots of different ways that you can demonstrate this, even using the same technique. That's why marking calculus is beastly. Okay, so I'm asking here to demonstrate. So what this question is really asking us is it's asking us to demonstrate that vector P can be written as A times vector N plus B times vector N, where A and B are both members of the reals. Okay, so in essence, let's write this a different way. We're going to say, well, that really means that -4, 5, 3 is equal to A times 6, 3, -1 plus B times 3, 5, -4. That's not a negative. 3, 5, and -4. Okay, so lovely. So what we're going to get out of this is, hopefully you can spot right away, we're actually going to get three equations here. So if I think, and I'm going to write them, over top of one. So the x's generate the following equation. It says that -4 is equal to 6a plus 3b. The y's generate the equation 5 is equal to 3a plus 5b. And the z's generate the equation 3 is equal to -a minus 4b. So I got three equations here, and there's only two unknowns. So I need to solve for a and b here. You can choose any two. Again, what leads us to a challenge when I'm marking this is I can choose any two. I could choose these two, I could choose these two, these two. It doesn't really matter. I'm going to take two of them and I'm going to be consistent and I'm going to fully solve the system with those two. It's really, really important, and this is where kids often go wrong, is that I'm going to use maybe these two to solve for A. I have to substitute back into those two to solve for B. If you use these two to solve for A and then you substitute into this one to solve for B, you're not going to get you might get the right answer, but it would be coincidental, right? So you need to choose the two you wish to work with and be consistent about those two. So if I called this equation 1 and this equation 2 and this equation 3, I think I'd probably use equation 2 and 3, simply because equation 3 I can multiply by 3 and then use elimination method really, really easily. So I'm going to do that. So I'm going to say equation 2 just gets to be equation 2. So it's 5 is equal to 3a plus 5b plus 5b. And then I'm going to take equation 3 and I'm going to multiply it by 3. So 3 times equation 3 is going to be 9 equals negative 3a minus 12b. And then I am going to add. So I guess that would be 14 is equal to negative 7b. Divide both sides by negative 7, divide by negative 7, and we find out that b is equal to negative 2. So easy peasy, we're all good there. Now, again, this is the key. It's really important that we substitute it back into either equation 2 or equation 3. If you put it into equation 1, doesn't really look like a 1. If you put it back into equation 1, you could definitely end up with the wrong answer. So you need to choose 2, stick with it until you have solved the system. So I'm going to substitute that back into equation 3. So subbing into 3. Okay, so it's going to be 3 is equal to negative a minus 4 times negative 2, and then we're going to solve. So I'm going to move the a over so it becomes positive. A is equal to, and move the 3 over so it becomes negative 3 plus, I guess that would be plus 8, I think. And so we have that a is equal to 11. Now, those are the two values. And you're like, okay, it's consistent, lovely. First off, I just want to check this in the equations that I had just to make sure that I didn't make a mathematical error, because you guys aren't around to pick up on those things for me. So that would be 33, is that right? So 33 minus 10 would be 23, which is not 5. Oh dear, I've probably made a mistake somewhere, have I? Oh, that's negative a. That's a, and that's 8. So that's 11. Yeah, I think that's good. So if I did that, so that would be negative 11. Yeah, okay, so that's good. And then put it in here. So that would be 33 minus 10 is not equal to 5. What did I do? I made a mistake somewhere. Okay, so let's pretend this is good. So what we're going to do is what we have is we have a consistent solution. And I think I may have made a mistake in my algebra, but the fact remains that in theory, we have a consistent solution for these two equations. If the third equation that I did not use in these two equations holds with these two values, what it means is that these three things are coplanar, because I have found a value that makes this true. Okay, so I want to go back, and I'm sure I made a mistake. I will check this afterwards, but what we're going to do is I'm going to then check in the third unused equation. Okay, so we're going to check in a third unused equation. So I used equation 2 and 3 to solve, so I'm going to check it in equation 1. Check with 1. So my left side in 1 is it's just negative 4. My right side in 1 is 6a plus 3b. So left side is just negative 4. We're all good there. And then, so what we would have is 6 times 11 is what I got for my a value. Did I put it in the wrong spot? B. I don't know. Oh, yeah, that's my problem. No. What? That moved over. That moved over. Oh, so that's negative 3. There's my problem. Yay, I found it. That's negative 3 because that moved over. So that's going to then be 5. Okay. Better, better, better. My apologies, guys. So A is 5. So I'm going to check and I'm going to put the 5 in here. So I need to clear that up. I knew there was a mistake in there somewhere. There may be another one, but let's pretend that it's good. So A, my value is 5, and then B is going to be 3 times negative 2. And so that is going to be 30 minus 6, which is 24. So the left side does not equal the right side. So from that conclusion, I can conclude then, therefore, the three vectors are not coplanar. If this had have come out that they both had the same value, and again, there's a decent chance I've made a mistake along the lines here. If it came out that they did match, that would mean that we were able to demonstrate the third vector was in fact a scalar multiple of the original two, making them coplanar. Okay, so lots to digest there. I'm going to give you some practice questions right here because this lesson followed very much along the lines of what I would do in class. I thought that this is a really relevant lesson. So this is going to be from page 340, numbers 2, 6, 10, and 14. And again, folks, no one is asking me for clarifications on any of the stuff so far. I would encourage you that, if any of these questions are not ringing true to you and you're having difficulties or you want additional clarification, by all means, reach out and ask me, and I'm happy to either set up some one-on-one time or some class-wide time or just create a custom video for that purpose. Okay, thanks, everybody.